Hello, welcome to Castro in the Classroom. My name is Rebecca McElroy and I'm a PhD student at the University of Sydney.
Hi, I'm Associate Professor Tara Murphy and I'm an astrophysicist at the University of Sydney.
Today, Tara will be giving a presentation called Waves in the Sky. You can send in questions during the presentation using the Twitter hashtag Castro17, and Tara will answer some of your questions at the end. I'll be back a bit later, but for now, here's Tara with Waves in the Sky.
Thanks, Rebecca. So my job as an astrophysicist is to search for extreme events in the universe, like the moment when a black hole forms, and work out what's causing those events. Before we start, I want to tell you a little bit about how I got to this position. My first memory of being interested in science was getting £5 as a present from my grandparents when I was a kid, and looking at this book on the top shelf of the bookshop and asking my mum if I could get it. She wanted to know if I was really sure that I wanted it, and I ended up reading it hundreds of times while I was in primary school. The other thing that happened early on in primary school was that my school got a BBC microcomputer, and when I finished my work, I was allowed to go and play on the computer in the corner of the room. I think I spent most of my time playing early text-based role-playing games, but it piqued my interest in computing as well as in science. Jumping forward many years, I did a science degree and then went on to do a PhD in astrophysics. Now I think I've got the coolest job in the world. I get to travel to telescopes, to conferences, to talk to other scientists. I get to work on massive supercomputers and work with really great students. So, if you have any questions about becoming a scientist, I'm happy to answer them afterwards, but now let's get into the science. So in 2015, I had a really talented student who made an amazing discovery. You might have seen this picture on newspapers around the world of these giant plasma tubes around the Earth that she discovered. Today I'm going to tell you about how she made that discovery, a bit about how science works. How do scientists actually discover new things? And when we've found new things, how do we know that they're real? Let's start with the first character in our story, the Murchison Wide Field Array Telescope, or MWA for short. New discoveries are often enabled by new technology. Why? Because it allows you to explore things that you haven't been able to explore before. The MWA telescope was designed to answer some specific questions, such as, how did the first stars in our universe form? But as well as those specific questions, we try to design the instruments so that they can make unexpected discoveries too. And this is what scientists call serendipity. The MWA has lots of special properties. It observes very low frequency radiation, and it can see almost the whole sky at once. But one of its really special properties is where it's located. The MWA is way out in the Western Australian desert. Why did we build it right out there? The reason is every single electronic device you have emits radio waves. Your phone, your TV, your microwave. Our telescope is super sensitive. It's so sensitive that if you put your mobile phone on the moon, it would still be one of the brightest sources in the sky to our telescope, brighter than all of the galaxies and stars out there. So imagine what it's like if you had the mobile phone right next to the telescope. That's why we have a really big sign right at the edge of our observatory that says Radio Quiet Zone. This is a special place where you're not allowed to take any electronic devices. You're not allowed to bring a mobile phone, a radio, or anything else like that near our telescope so that we can detect these sensitive signals from the sky. Now, running a telescope in the middle of the desert isn't easy. Building the antennas is actually not the most difficult part. You can see here some of the students working on building them. But there are loads of scientific and engineering challenges, such as how we provide power in the desert, how we transport terabytes of data back to Perth, and how our engineers can work in 40-degree heat. So we've built our incredible telescope. What do we actually want to do with it? Everything you see in space is because it either emits or reflects light. But when you think about that, you're mostly thinking about visible light. That's the light that our eyes have evolved to be able to see, and it's hundreds of nanometers long, which is very tiny. What our telescopes see is radio light. Radio light is centimeters to meters long, very long wavelengths. On Earth, we use radio waves for communication, for radio, for TV, and for wireless internet. We often say that radio waves reveal the invisible universe because they see processes in space that visible light doesn't let you see. For example, gas in galaxies, supermassive black holes or pulsars are all revealed by radio light. This image shows radio and X-ray images of supernova remnants. When massive stars die, their core collapses and a huge explosion blows out all the stellar material into space. This is called a supernova. As that material travels into space, it creates a massive shock, and that shock accelerates electrons, which emit radio waves that we can detect on Earth with our telescopes. So before I tell the next part of the story, I wanted to think for a moment about how science actually works. Probably at school, you've thought about two types of science. You've probably thought about theoretical science, where, for example, someone like Einstein uses equations to make predictions about the universe. You might have also thought about experimental science, and you've probably done some experimental science in the lab, where someone like Curie is discovering new elements. We think about experiment and theory working in sync with each other, predicting and then confirming those predictions and discovering new things about the universe. But in astronomy, we can't experiment. We can't take the sun and turn it off and turn it on again to see what happens. So what can we do instead? We can do a different type of science. We can conduct observations and we can run simulations to discover how the universe works. I want to explain a really quick example that's not in astronomy of how we might design an observation. Imagine your aim is to work out how long lions live. What's their life cycle? What's the life of a lion like? But there's a catch. You have to do this research in only one day. That's a little bit what it's like being an astronomer. We only have decades to do our research, but radio galaxies last for millions of years. We can't watch one from its birth to its death and figure out what's going on. So what could we do with our lions? We could go out into the grasslands for one day, and we could count how many baby lions we find. We could count how many teenage lions we find. We could count how many adult lions and how many dead lions we find. And from this information, we could build a statistical picture of the population of lions without ever seeing one lion be born, grow old, and die. We have to think of clever ways in astronomy of observing the universe and clever ways of working out things about how things work in our universe. So that brings me to the problem that I was trying to solve. When we look at the sky through a radio telescope, it's mostly static. If you look at this image, each of the black dots is a distant radio galaxy. That means that in each of those black galaxies you see, there is a supermassive black hole at the center, and as it accretes matter, in other words, gobbles up stars in that galaxy, it emits radio waves, and so we can see it from far, far away. Now, we wanted to work out how much radio sources vary, how much galaxies vary with time. But there was a problem. The ionosphere of our own Earth actually makes the galaxies look like they're moving. So when we look with our radio telescope, you see a movie like this. It looks like all the galaxies are jiggling around. Now, this is really important. The galaxies are not actually jiggling around in space. The ionosphere acts like a screen between us and these galaxies, and so it distorts the image and makes it look like the galaxies are moving. What's this ionosphere that I'm talking about? The ionosphere is a region of the Earth's atmosphere that's 80 to 1,000 kilometers above the surface. So in this image, you can see where aeroplanes and space shuttles travel to, and you can see that red band that shows you where the ionosphere is. The ionosphere is a special bit of the atmosphere where the sun's radiation has ionized the atoms. In other words, they've lost some of their electrons. But the important thing for our story is that while radio galaxies are millions of light years away, the ionosphere is right in our neighborhood, only a few hundred kilometers up above Earth. So the question I asked my student was whether she could work out how the ionosphere affects our observations of these distant galaxies. So now the next character in our story is the student herself, Cleo Loy. So she was an undergraduate student, only a few years older than you watching this video. And she was very keen to do something with our new telescope and also to do something with large data sets and understand the physics that was going on. So one of the first ideas that she had, which is really great idea, is could we use the radio galaxies as kind of backlights to look at what's going on in the ionosphere? So we know these radio galaxies don't change. So any changes that we see in them are due to things like the ionosphere getting in the way. So Cleo had some pretty good coding skills. And so she took the data from our telescope, and these data sets are huge. We have terabytes of data coming from the MWA. She took the images from those observations, and she made a little arrow at the position of every single radio galaxy. And then she took the observations through the night, and she worked out how those galaxies were moving through the night. Remember, they're not really moving. They appear to be moving because of the ionosphere. So she produced these plots, and we had no idea what we were going to see when we looked at them. When we did look at them, we saw something very, very strange. So rather than jiggling randomly on the sky, the movement of the background galaxies was actually making patterns. So there was something going on with the ionosphere that was making these patterns in our image. So each of these blue and red arrows in these plots are the position of the radio galaxy changing with time. And if you look at that plot with the stripes, this was a really unexpected result. There seems to be some really strong striping going across the sky. Now, as an experienced radio astronomer, when you see something like that, your first thought is, there's something wrong with our data. And so Cleo sent these results round to our whole collaboration. Now, in science, we often work with large teams of people, and our collaboration has hundreds of scientists and engineers around the world who all work together on this telescope. She sent it to the collaboration, and people were very excited. I think she had 50 emails back that weekend. But most of them suggested there was almost certainly something wrong with the data. We thought, could it be a broken tile on the telescope? Could it be something wrong with our calibration? Could it be really bad weather that's behaving in a strange way? We had no idea what it was, but we were almost certain it wasn't real. So that started a months-long quest to find out what the problem was in our telescope. And Cleo, as a new student, was very enthusiastic and very questioning, but at the same time was drawing on our experience of saying that there was something that wasn't right. And so she was trying to debug it. After many months of email exchanges with hundreds of scientists, we had eventually ruled out every possible suggestion that they made, and Cleo had very diligently tried out all of their suggestions, and none of them could remove this effect. So she started to believe her instinct, which was that it might actually be real. There might be really stripes in the sky. What was going on? So she did a lot of reading of physics textbooks and other papers in the literature and started to think, maybe this is nothing to do with astronomy, those distant galaxies. Maybe this is something to do with something really close to home, our own Earth. And she had just a sort of random idea to try putting on the plot the Earth's magnetic field lines. And bingo, the Earth's magnetic field lines lined up exactly with the stripes that she was seeing. So now there was some really compelling evidence that this was actually something to do with our own Earth's magnetic field. But let's think about where we've got to so far and how we actually confirm things like this in science. So far, we've done some observations. We've found some really interesting patterns in those observations. We've ruled out artifacts, we've ruled out errors. We've tried different data sets and seen the same thing, so reproducibility. We've checked with other scientists, we've investigated all their suggestions from several hundred scientists, and none of them would work. We've read other scientific papers in the literature, and finally, we've come up with a hypothesis. We did some calculations that showed this hypothesis seemed to be real, but we can't prove it. We think we're seeing plasma tubes in the ionosphere, but how can we actually find more evidence to support this hypothesis? The next idea that Cleo had was really, really exciting. No one had ever used our telescope in this way before. And I'm going to let her tell the rest of this story in her own words.
Due to its molten iron core, the Earth has a magnetic field around it, just like a bar magnet. This magnetic field extends outwards into space, forming a big bubble that we call the magnetosphere. The inner layer of the magnetosphere, from near the Earth's surface up to 1,000 or so kilometers, is called the ionosphere because it is made up of particles ionized by radiation from the sun. In low-frequency radio astronomy, when we point our telescopes to the sky to measure the faint signals that travel through space to reach us, we need to take structures and perturbations in the ionosphere into account that might change these signals. We need a good understanding of the effects of the ionosphere to make sense of our data. Pictured near the surface, the Earth's magnetic field lines run parallel and come out at an angle to the ground. It has long been postulated that tubular plasma structures go along the magnetic field lines, and it is structures like these that can affect our astronomical measurements. Previously, people could only guess what they might look like, since no one has ever been able to image them. My name is Cleo Loy, and I am an astrophysics student with Castro at the University of Sydney. I have found that we can use a new type of radio telescope to not only detect these plasma tubes in the ionosphere, but to actually image them. And what's more, we can reconstruct their behavior in real time and in 3D. This is a very exciting world's first. The Murchison Wide Field Array, or MWA for short, is a radio telescope in the Western Australian desert. It consists of 128 receiver tiles, spread over a circular area roughly 3 kilometers across, that work together as one instrument. What makes it so special is its huge field of view, letting us observe a large patch of sky and all sorts of celestial objects as they flash or pass overhead. We use the MWA to study how the ionosphere shifts around the observed positions of objects in the sky and distorts them. A good analogy for this is the way lights at the bottom of a swimming pool dance around when the water ripples. We cannot see the water directly because it is transparent, but from the dancing lights we can determine the pattern of the ripples at its surface. Just like when we are looking at an angle down parallel train tracks, if you were standing at the site of the MWA, the Earth's magnetic field lines would appear to converge. What we saw with the MWA was a stunning distortion pattern that strongly coincided with the magnetic field lines. For the first time, we revealed the true nature of these structures as a vast array of plasma tubes, filling the sky in staggering numbers. The MWA's rapid snapshot capabilities allow us to make movies showing their motions over time. But that's not all. The MWA also has the power to see in 3D. When we look at an object, our brain combines the images from our two eyes, allowing us to judge how far away it is. So by analyzing the signals recorded by MWA tiles in the east, separate to tiles in the west, we give the MWA the ability to perceive depth. This has never been done with a radio telescope before. By using the MWA like a pair of eyes, the three-dimensional nature of the tubes springs into reality. We can measure their heights above the ground, see their steep inclination, and watch as they drift sideways towards or away from the MWA. This is a whole new way of looking at the sky.
So that was how Cleo made the final bit of evidence that we needed to show that these waves were in the ionosphere. Why had no one thought of using a radio telescope to do parallax like that before? If you've studied parallax at school, you'll know that it only works for things that are really close to us. Distant radio galaxies are too far away for parallax to work. So people who'd worked as radio astronomers our whole careers had never thought to use this technique. But a new student coming into this with no preconceptions was able to make that conceptual leap that we didn't think of. So it was a great breakthrough to do that. The final step of the process once we had this evidence is to publish it. Scientists publish their results so that after we think internally that we think the result is right, we want to ask all of our peers what they think too. And so a published paper is just part of the conversation with the rest of the scientific community, where we say, we think this interpretation is right, what do you think? And then other people write other papers in response. So Cleo was able to publish 5 papers describing this work that other scientists are now using in their own work and responding to. So I hope that you found this story interesting. We've taken a new telescope, amazing new technology, in the Western Australian desert. We've taken a student, only a few years out of high school, who was very good at physics, but had the kind of curiosity and lack of preconceptions that made her to make these leaps that we couldn't make. And the other thing to point out is she had great coding skills, so she was also able to analyze this data herself. So when you combine new technology with curiosity and the ability to analyze the data, you have the potential to make new discoveries. I encourage you, if you're interested in pursuing a career in science, to keep going, to remain curious and excited about what you might discover. Maybe the next breakthrough will be yours. Thank you.
Thank you, Tara. That was a fantastic story and gave us so much to think about. So now we've got some questions that have come through during your presentation. So first up, can you tell us a little bit more about radio waves?
Yes, so you might have studied the electromagnetic spectrum. Electromagnetic radiation comes in every wavelength, from very, very small wavelengths to very long wavelengths. Radio waves are at the low energy, long wavelength end of the spectrum. They're really safe. They travel through almost all material, but don't impact it at all. One of the reasons that radio waves are so special is that they travel through dust in the universe, and so we can see into the center of galaxies, which in optical light is obscured and you can't see. So radio waves are a very special form of electromagnetic radiation.
Okay, thank you. So the next question that we have is, how are black holes formed?
Okay, so I mentioned two types of black holes in my talk. One of them, what we call normal stellar mass black holes, are formed when a massive star gets to the end of its life. It burnt up all of its material and it dies by the core collapsing into a black hole while it blasts off all of the other material into space. So black holes can be formed when a star collapses and the matter at the center becomes so dense that it's considered a black hole.
Okay, interesting. So will the sun ever become a black hole?
So that's a good question. You notice in my explanation I said massive stars. So how a star ends its life is determined by how massive it is. Massive is a word that means how much it weighs, okay? So really massive stars, giants and supergiants, they end their life in violent explosions that often result in a black hole forming at the core. But more moderate stars like the sun, they have a less dramatic end. And what will probably happen to the sun is that eventually it will run out of fuel, collapse and form a white dwarf star rather than a black hole. So we won't end up with the black hole. No.
Okay, so a little bit less to worry about. So you mentioned shocks when you were talking about supernovae. Could you explain what those are?
Yeah, so a shock is, if you imagine, you've probably seen footage of an explosion, for example, on TV. A shock is when material traveling extremely fast into some other medium has a really sharp edge that causes, it could be in sound, it could be sound waves, it could be radiation, and that shock can travel through space so that we can detect it elsewhere. So in the context of supernova, what that is the material from the star hitting the interstellar medium, all of the gas around the star, and that causes a shock.
Okay, so changing gear a little bit, another question that we have is, do you think we'll ever find life on another planet?
Oh, isn't this one of the best questions? I mean, this is maybe what many people consider the ultimate aim of astronomy is, are we the only life in the universe? Before I answer, I have to say, when I was at high school, we'd only just found the first extrasolar planet, so a planet outside our solar system. So until the late 90s, we thought that the planets in our solar system were the only planets in the whole universe, and we were pretty sure there was no life on the planets in our solar system. So when we first started discovering extrasolar planets, this completely changed our view of the universe. And whether there's life on them is really a matter of balance between what we know in astronomy, where we know that there are billions of stars, and we now know that many, many of those stars have planets, and that's just from exploring the tiny bit of our galaxy that's around us, versus biology, where we know that the formation of life is extremely difficult and very rare, most probably. So we have a universe where we know there are many, many planets, and we have a biology saying that forming life is very, very difficult. Which of those will win? I'm an astronomer. I reckon there's probably other life in the universe.
Cool. So, do you think we're going to find other planets that are just like Earth?
Yeah, so this is one of the big missions of current exoplanet research, is we've now found planets. We know about 3,000 planets outside our own solar system. How many of those are like Earth? Well, I think the first question is, what does it mean to be like Earth? We are a rocky planet, so you can actually you can stand on us. You can't, for example, stand on a gaseous planet. It has no surface. We're close enough to our sun to have the warmth to support life, and so we're not too close to be too hot. We're not too far away to be too cold. And importantly, we have an atmosphere. The magnetosphere, the ionosphere that I was talking about, they protect our Earth from the damaging radiation from the sun, like solar flares that would wipe out things, all life. So basically, to find another Earth, we need to find a planet that's in the habitable zone. It's not too close, it's not too far, it has an atmosphere to protect us, and so that would be the first step in trying to determine whether we've got another planet like Earth.
Okay. So related to that, do you think humans will ever be able to live on another planet than our own?
Well, that's a very different question. So I get asked this a lot. One thing to keep in mind, we've now actually discovered a planet around our very closest star, Proxima Centauri. But how far away is our closest star? It's 4 light years. It would take us a long time to travel to our closest star. We have no technology at the moment that would allow us to do that. So let's assume for now, in our lifetimes, that we're not going to be traveling to a planet outside our own solar system. So that leaves us with the planets in our own solar system, in our lifetime. Could we live on another planet? I think we all know that the most likely candidate is Mars. Venus has a terrible poisonous gassy atmosphere, and the other planets are too cold, or too hot. So Mars is our closest friend. I think it's very exciting. I think it's very expensive. I'm sure it's possible. The question is whether we would decide to do that. Yeah.
Okay. So there's been a few questions related to your work as a scientist. So what did you actually study to get where you are?
Yeah, so at high school, I started out doing physics and chemistry and maths at high school, but I also loved English and humanities as well. So I was a bit of a generalist. Lots of scientists like lots of things. When I went to uni, I was actually tossing up between an arts degree and a science degree because I really loved both, and I ended up deciding to do science. I actually thought I was going to do biology, so I started my science degree. I did a bit of biology, a bit of chemistry, a bit of physics, a bit of maths, and at the end of first year, I really found that physics excited me the most, and so I went on doing physics and maths and just kept pursuing what was most interesting to me until I found myself with a PhD in astrophysics.
Okay. So what inspired you in particular to go into astrophysics rather than any other area?
I suppose my 2 favourite sciences were astrophysics and biology. Okay, so I probably liked those the most. I think I've always liked the philosophical question of, a bit like what you're asking about the planets. How did we get here? Who are we? What's our place in the universe? And so thinking about those big questions was what really attracted me to astronomy. What I didn't know at the time was that one of the challenges of modern astronomy is dealing with the massive data sets that come off new telescopes. And so I also love coding and I love analysing data. And so it turned out that the practical day-to-day work of being a scientist in astronomy was actually very interesting too. It's the type of problems I like solving. So I like thinking about the big picture, but I also like doing the analysis that you need to do in astronomy.
Okay. And what do you think are the advantages of actually studying physics and astrophysics, even if you don't want to become an astrophysicist?
So a lot of people study physics and astronomy and don't go on to become scientists. And I teach a lot of undergraduates in physics and astronomy and computing at university. One of the great things about those skills that you learn when you're doing a subject like this is you learn how to solve problems. I know it sounds like a cliche, but you learn how to solve new problems that other people haven't solved. You learn how to think about problems in different ways. You learn how to manage information, manage data, and work out things from data. Those skills are actually really important in all kinds of careers. A lot of our graduates at the University of Sydney go on into careers in finance, they go on into careers in engineering, they go on into careers in all different areas of life, not just science. And that's because the skills they've got are actually really good general skills. Computational thinking, problem solving, analytic skills that will set you up for any career.
Okay. So what do you think are the most exciting things going on in astrophysics at the moment currently?
Okay, so I think there's 2 really exciting things that are happening right now and that you might see the answer to in the next 10 years. The first one we've already mentioned is exoplanets. The Kepler space mission completely revolutionized exoplanet astronomy and our understanding of the universe, discovering these 3,000 exoplanets. Now we know they're out there. The hunt is on for whether they could sustain life. We're building telescopes that will be able to detect water in the atmosphere of extrasolar planets. And that's probably going to be the next big breakthrough, is finding a planet that's like Earth, that has water, and that hence might be able to sustain life. So that's the first one. The second one is a completely different end of the spectrum, and most people consider this the biggest breakthrough in physics of this century so far. And that, of course, is the discovery of gravitational waves. Gravitational waves were predicted by Einstein over 100 years ago, but there was no direct detection of them until last year. So with this incredible instrument called LIGO, a massive interferometer in the US, scientists managed to discover gravitational waves from a system of binary black holes that were orbiting each other. So two black holes that are orbiting each other. And as they get close enough, they actually emit waves that cannot be detected by any normal telescope, but that can be detected by a gravitational wave detector. This confirmed the last prediction of Einstein to be correct and opened up a completely new window on the universe. We don't know what we're going to see. That is what most people at the moment consider to be the most exciting discovery of our time, and I think that that will carry on for the next decade as being an incredible area of research.
Yes, definitely. So what's the next step from LIGO?
So the next step, the problem with current gravitational wave detectors is they're very bad at knowing where the source comes from. So they know that two black holes somewhere in the universe have coalesced and released these gravitational waves, but they have no idea where that occurred. Well, not within hundreds of degrees. So the next step is another instrument of a similar type called Virgo. And when you combine those two together, you'll actually be able to narrow down where these things are coming from. And then we'll be able to start detecting things potentially like primordial black holes that formed at the very beginning of the universe. And that will show us how galaxies formed and a whole load of other things. So the next step is a new instrument and combining that information together.
That sounds very exciting. So would you like to tell us about the next phase in your area of study? Square kilometre array, perhaps?
Yes. So the Murchison Wide Field Array and another telescope I work on also in Western Australia called the Australian Square Kilometre Array Pathfinder are both telescopes that are prototyping a huge telescope called the Square Kilometre Array. It's called the Square Kilometre Array because it will have a square kilometre of collecting area, which means, it's a very technical word, it means it will be able to detect really faint sources in the distant galaxy. With that telescope, we're hoping to be able to detect something I hinted at in the talk, which is called the epoch of reionization. The epoch of reionization is when the very first stars formed in our universe. So back at the beginning of the universe, we have some pretty good theories about how the Big Bang happened. And when we look in what's called our local universe, we can see how galaxies got to where they are now. But in the middle, there's a period we call the Dark Ages, after the cosmic microwave background radiation and before the galaxies we see now is a period of time which we have not been able to investigate. The Square Kilometre Array will let us investigate those dark ages and potentially see the very first stars that formed in our universe.
Well, that sounds incredibly exciting.
It is. I'm really excited.
So I think that's all the questions we've had. Thank you so much for tuning in, and thank you again, Tara, for your fantastic presentation. So thank you. That's it for Castro in the Classroom today.
Thank you, everyone.